Hey everyone. So in this video, I'd like to say a few more things about transformations of sinusoidal functions, so transformations of sine and cosine. So one sort of transformation that we haven't really discussed is this idea of a horizontal shift of the graph of some function. And so if I add some quantity to my input of a function, if that quantity is positive, it's going to shift my graph to the left that many units, and if my quantity is negative, it's going to shift my graph to the right that many units. And so, for example, let's use this function f of x is equal to x squared. So here, the graph of this function looks something like this. And if I think about the function corresponding to x minus 2 squared, well, this is still squaring some quantities. It really just amounts to squaring some numbers. It's going to be a different number. And if I imagine, what number is going to give me this sort of vertex here, well, an x value of 2 is going to lead to that vertex point, right? If I have 2 input into this function, then taking away 2 is going to give me 0, and I'm going to square 0. But in everything else I plug into this function, it's going to square something larger, right? And so here, really, we can see just by checking the points that our function, when we when we subtract 2 to our input, really just amounted to shifting it 2 units to the right. And if you don't feel completely convinced, I would definitely encourage you to pause the video and just plug in more points, enough points to convince you that this subtraction in this input is going to shift our graph right. So let's look at a horizontal shift of the sine function. So here I've got this difference, this subtraction by pi over 2, and this is telling us that we have a horizontal shift of our function, our sine function, the graph of our sine function, and it's going to be a shift right by pi over 2. And so if I have my sine function where 0, an input of 0 gives me 0, and an input of pi over 2 gives me 1, an input of pi gives me 0, and an input of 3 pi over 2 gives me negative 1, and 2 pi is going to give me 0. My graph of this sine function, sort of the base function I want to compare to, at least one period looks like this, right? So this is not the graph of f of theta, this is the graph of y is equal to sine of theta. And so what I'm saying here is that this function is going to be a shift right by pi over 2 units. So here that point 0, 0, it's going to appear at pi over 2 comma 0. This point here of pi comma 1, that's going to come from shifting our point pi over 2 comma 1 right pi over 2 units. And really we see these points out here. I guess I'm missing one on my grid, but we can kind of picture it out here. Right, so here's a sketch of this graph, where this point here, well, if it's pi over 2 units to the right of 2 pi, this is going to be, well, what is that? That's 5 pi over 2. Right, 4 pi over 2 gives me 2 pi, and then pi over 2 on top of that gives me 5 pi over 2. Okay, so that's more or less what this shift looks like, and maybe to convince us, just this once, let's go ahead and make a table for it. So here, if I have a table where I have input values of theta, and I have output values f of theta, well, if I plug in 0 into this function, then I'm computing sine of 0 minus pi over 2. I'm computing sine of negative pi over 2. And negative pi over 2, that takes us clockwise around our coordinate plane to all the way to the bottom part of the y-axis. Right, so this brings us to, on the unit circle, a y value of negative 1. If I plug in pi over 2, well, then we have sine of pi over 2, take away pi over 2. In other words, sine of 0, so this gives us 0. If I plug in pi, then what we're really doing is we're computing sine of pi minus pi over 2, which gives us pi over 2 as an input for our sine, and this gives us 1, right? So these slightly larger values are giving us the same input for our sine function, or that we're used to, right? So here if I have 3 pi over 2, then we're really computing sine of pi, right? 3 pi over 2, take away pi over 2 gives us 2 pi over 2, or just pi, and that's 0. And then plugging in 2 pi gives us sine of 3 pi over 2, and that's negative 1. And then if I plug in 5 pi over 2, then really we're computing, not pi over 4, it's 5 pi over 2. And we're computing sine of 2 pi, and we get 0 out. Right, so here we can really see that we had to plug in pi over 2 units larger to really compute sine of the values we're used to. And if I have to plug in larger values, then I have to plug in values that are further to the right to get the same outputs. And so really our graph is going to be shifted right pi over 2 units. So let's take a look at another example where we have a combination of horizontal transformations. So here I see this scaling of our input by this factor of 2. And when we scale our input, that's going to give us a horizontal stretch or compression. And because this is scaling by a factor of 2, it's really going to amount to a compression by 1/2. And then we also have this horizontal shift by pi over 2, right? So shift by pi over 2. At least that's what it looks like at first. But I actually want to warn you from taking this perspective of this function here. So when we do a horizontal shift and a horizontal compression or stretch together, the order in which we do this actually matters. And usually, when we think about doing transformations together in the same direction, we want to do the stretch first. That's typically what we do when we're dealing with stretching and shifting in terms of our outputs. We sort of do the stretch first, and then we shift it. And this is because if I imagine stretching my function in the horizontal direction, really we're talking about stretching away from the y-axis. And so if I shift over first, then we're going to stretch really all that shift as well. And so really the way we want to graph this function so that we can kind of properly think of doing a stretch first and then a shift is actually to factor out the input. So really to graph this function correctly with a stretch first in mind and then a shift, we want to factor that input. In other words, we want to view g of x or g of theta as sine of well, I'm going to factor out that input. I'm going to factor it out by this coefficient of our input 2, but I'm going to factor it from that whole input, even the constant term. So here we have 2 times theta, take away, and if I'm going to factor out 2 from the constant term as well, I'm going to get pi over 4 here. And so really, if I wanted to graph this original function using the compression and the shift that I see originally, what we would need to do is compute or apply the shift first and then the compression afterwards, which is a little bit more challenging to do. And so I discourage this. I'm going to discourage this. Whereas here, if we factor out that input factor of 2, we can really still see that same compression by a factor of 1/2. And then we can see that horizontal shift by pi over 4 to the right. And with this factoring done, really this compression would be applied first, and then this shift would be applied second, kind of in our ideal way. So let's go ahead and graph this function. So here there are a few things to notice. I mean, when we've graphed these sorts of functions, we've paid attention to a few things like the midline. So because this function isn't shifted up or down, the midline is y is equal to 0. And the amplitude, well, the amplitude is the coefficient in front of the function, and that's just 1. So the amplitude, this is just 1. And then the period. Right, so the period is, well, it's 2 pi divided by the coefficient of our input, and that's 2 in this case, right? So here it's telling us that our period is pi, and that kind of makes sense because we're compressing our function by a factor of 1/2. It's going to get squeezed towards our output axis, or vertical axis. And so here, now that I know that my function is going to be also shifted to the right 4 units, I can kind of imagine, or pi over 4 units, that when I plug in pi over 4 into this function, it's going to really amount to computing sine of 0, right? If I imagine plugging in pi over 4 into this function, well, we've got 0, or pi over 4, take away pi over 4 is 0, 2 times 0 is 0, so sine of 0 gives us 0. And so at an input of pi over 4, we get an output of 0. And so, we know that the period is going to be pi units, so pi units to the right is going to bring us all the way out here, is going to be when we end our period. And so right in between is when our graph of sine goes, crosses from being positive to negative, and so here we can kind of expect to see the graph of this function to look something like this. But the main thing to notice is that here we had a compression and a horizontal shift, and to properly to apply both of these in combination, we had to factor out that coefficient of our input from both the input and the constant there, so that we can apply the stretcher compression first and then the shift afterwards. Okay, so let's go ahead and do another example. So I've got this function here, y is equal to 2 times cosine of pi over 3x plus 2 pi over 3, all take away 3. So please try and graph this function first. Make sense of what the midline, the amplitude, and the period are, what the shift is, so that you can graph this function. So here, I can see right away that this coefficient here, that's the amplitude. I can see that this minus 3 here, this constant, this is going to tell me the midline. I can see that this coefficient of our input, that's going to tell us our period. So this isn't our period, but it can help us find our period. And that 2 pi over 3, that's not quite our shift. We have to do some manipulation first, right? So here maybe I'll rewrite this as y is equal to 2 times cosine of, now if I factor out pi over 3, well, that's going to leave behind an x. And 2 times pi over 3, when I factor out that pi over 3, that's really just going to leave behind a 2. And so here we see that our period, well, this is 2 pi divided by pi over 3. And so to do this division of a fraction within a fraction, I'm going to multiply by the reciprocal of that second fraction. This is 2 pi times 3 over pi. And so those pi's are going to cancel out, and really the period is equal to 6. And what about the horizontal shift? Well, the horizontal shift is going to be left 2 units. Okay, so I can go ahead and try and graph this with all this information. The midline is y is equal to negative 3, so I can kind of imagine this is sort of the what's the word for it? Just some structure to sort of start with. And then the amplitude is 2 units, so I know that we're going to fall in this region here. we're dealing with our cosine function, so I can imagine that we're starting away from our midline and sort of going back and forth, up and down across this midline. And so because we're shifting left 2 units, I can imagine that, normally I would expect my graph to start here for our cosine function. It sort of starts, the amplitude above the midline, but because we're shifting left 2 units, it would really begin here. Right, if I were to plug in -2 into this function, we would get -2 plus 2 would give me 0. 0 times pi over 3 would be 0, and it'd be like plugging in 0 into our cosine function. Right? Plugging in -2 would be equivalent to inputting 0 into our cosine function, and we would get that point there. And then because our period is 6, I can see that 6 units to my right, I would sort of wrap up one period of my function, one cycle of my function. So 2 units to the right and then 4 units further gives me 6 units in total. And so that's when I expect my cycle to end and my function to repeat itself. And then right in between is when our function is going to be at its lowest, right? Cosine sort of starts high, makes its way down, and then back up. And so here, just a rough sketch of this function. Looks something like this. And then it continues onwards. But right, having all of our structure, knowing the midline, the amplitude, the period, and the shift really gives you so many tools to graph this function without having to plot a bunch of points. So here, I want to do the reverse. I have this function, this graph of this function, and I want to figure out some equation for this function. And so please pause the video and see if you can use our ideas we've discussed so far to come up with an equation. So there's definitely multiple equations that would work out, but let's find the amplitude, the midline, and the period just to give us some sense of what we're working with, and let's see from there, does it make more sense to look at this as a sine function or as a cosine function, and we'll be able to use all of that information to figure out some sort of equation. So it looks like the midline, this horizontal line that's right in between the peaks and the valleys of this function, is the horizontal line y is equal to 2. We also see that the amplitude, that's this distance here, well, that's an amplitude of 4, right? So this is our amplitude. And then our period, it's when this function repeats itself, and I can kind of think of it as when I go from one crest or one peak to another. Right, so this is the period. And this is, well, if I'm kind of starting an x value or an input value of -1, and I end one cycle at an x value of +7, it looks like the period is 8 units. And so here, it depends on where you're trying to imagine starting this function. Maybe we can imagine starting this function here. Right, so this function's, if I imagine starting here, I'm going to kind of treat it like a sine function where my function starts at the midline, and then it goes down, and then back up, and then down, and then back up again. So, our function, for our sine function, typically goes, up and then down first. And so this would correspond to a reflection of our sine function. So here I can kind of also imagine that there's a reflection going on. So maybe just to start putting things together, we see that we've got an amplitude of 4. I'm going to deal with a sine function here. We haven't quite figured out the period. We have the information to figure it out, but I'm going to write a constant there just because we haven't determined it quite yet. B times x, and is there some shift? So we're not looking at a start along our vertical axis, and so there's going to be some shift. I can kind of view this as a shift right by 1 unit. So here that's going to be x take away 1, right? -1 is a shift right 1 unit. And then lastly we have this midline as y is equal to 2, so this is +2. And then lastly, we said that our function for sine goes up and then down and then back up. And so here, because this is going down first, it kind of looks like a reflection of our sine function. So I'm going to include this negative sign outside. And so now the last thing we need to figure out is this coefficient b. And so if the period is 8, and we know that we compute our period by computing 2 pi divided by b to get 8, well, I can multiply both sides by b. I can divide both sides by 8. And so b is equal to pi over 4. And so maybe I'll just rewrite this one more time. This is y is equal to negative 4 times sine of pi over 4 times x take away 1 plus 2. So this is one equation for this graph. There are many others. You can kind of imagine trying to fit a cosine function into this bill if you sort of imagine starting at this point. This would amount to a shift left, but we would still have the same amplitude without a reflection, without a vertical reflection. We would have the same period, just a different shift, but we'd also have the same midline. So there's many different ways you can write this same, an equation for this same function, the same graph here. Okay, so the last problem I'd like to go over is this very wordy word problem. So here this says the outside temperature over the course of a day can be modeled by a sinusoidal function. So suppose you know that the temperature is 50 degrees at midnight, and then the high and the low temperatures during the day are 57 degrees Fahrenheit and 40 degrees Fahrenheit respectively. So if T represents the number of hours through the day into the day since midnight, we want to find a function for the temperature we're calling D in terms of our hours T. And so there's a few things going on here, but one thing is we're saying that our temperature can be modeled by a sinusoidal function, right? It kind of makes sense that our temperature sort of, the temperatures of day to day sort of look very similar, kind of repeat themselves and go up and down. And it feels reasonable to say that we can model them with a sine function or a cosine function from one day to the next. And here, if I imagine, maybe I'll start drawing some sort of graph to work with here. If this axis corresponds to T, and this axis corresponds to our temperatures, and I imagine starting here at when T is equal to 0 at midnight, right, that's what 0 T represents, the number of hours since midnight. Here this having 50 degrees to begin with, and knowing that we sort of fall in this 7-degree interval away from 50 degrees, so here up to 57 and down to 43, that's telling us that our temperatures sort of oscillate up and down around this 50-degree mark. And so we're saying that this function, it starts at this midline. Its temperature starts at this midline value of our outputs, or temperature values of 50, and sort of makes its way up and down or down and up. And so if T is equal to 0 corresponds to when or corresponds to midnight, then we kind of expect our function to repeat itself maybe the next day after 24 hours, sort of the next midnight, right? I kind of imagine that from one day to the next that the temperatures will look pretty similar. And after midnight, do we expect our temperatures to increase or decrease? Well, as we're getting further into the night, our temperatures should decrease more, right? There's not really much reason for the temperatures to increase. And so we can kind of imagine that our graph probably looks something like this. And so here it looks like maybe it would continue onwards and probably started earlier. Here it looks like that the period, a reasonable period for this function would be 24 hours. So it looks like we've got an amplitude. Maybe I shouldn't have really bracketed this whole 14-degree interval. It should be 7. We've got a midline corresponding to 50. We've got a period of 24, and it looks like we're dealing with a sine function here. And so here I can imagine that the graph, or sorry, this equation, this function corresponding to this graph, corresponding to this scenario, it's going to have 7 times sine of our period, not our period, some constant that's going to determine our period, times t. Well, there's actually no shift left or right, so maybe I'll just write times t here without any extra parentheses, plus 50. And another thing we notice, kind of like our previous example, is that this function goes down first and then back up. So this would be negative 7 times sine of b times t plus 50. Right? Our typical sine functions go up and then down first. So here this looks like a reflection of a sine function. So again, let's figure out this constant here. So we're expecting our period to be 24 hours, and we know that our period can be computed by taking 2 pi and dividing it by the rate which we're traversing our inputs. And so here, if I take 2 pi and divide it by b, I expect to get 24. And so multiplying both sides by b, dividing both sides by 24, I get 2 pi over 24. And that's the same as pi over 12. So maybe I can rewrite this function again as d of t is equal to negative 7 sine of pi over 12 times t plus 50. So this is one way we can write an equation that really models the scenario we're given.